All right, welcome everyone. So today's session in the reinforcement learning series is about temporal difference learning. This is really the crown jewel of reinforcement learning. So I'm very excited that we get to talk about TD today. Um, if you understand um, the material that we've covered up through today, really, I think, about 3/4 of all the reinforcement learning papers out there, you've got enough, you're armed with enough to really understand what's going on with those. So just to recap again, I'll be your discussion leader, but this is really for everyone. So feel free to unmute, ask questions, feel free to use the chat. Have this just be more of a community event. Today's agenda, going to do a quick recap of the um, other topics we've talked about before, just to quickly level set, and then we're going to dive right in and introduce temporal difference learning. And so with the temporal difference update, we'll be able to talk about the basic TD0 algorithm, and then we'll talk about SARSA and Q learning, which are the basic building blocks for real reinforcement learning that people are doing today. So, okay, here's our quick recap, right? In reinforcement learning, we've got an agent working in an uncertain environment, and the only feedback it's getting is this reward signal. It's just a scalar number, positive or negative number. It's not a lot of information. And every time you take an action, you get this feedback, you get the number, but that's not what we're really interested in. We're interested in the long-term return, not just the individual reward after each single action. So what we do is we model this as a Markov decision process. In this case, you have the different states and you say that it doesn't matter how you got to a particular state. What happens from a given state only depends on the fact that you're in that state. So you need to encapsulate whatever information is important into the different states. And what this can tend to do for complex problems is cause the number of states to explode, to be very large. Sometimes I like to see Markov decision processes as graphs. For me, sometimes visual is a little bit easier. And then we have our different notation. The key ones are V is the value function for returns from a given state. So if you're in state number 17 and you go and you do blah, 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 blah as your next actions and you follow this policy, then what is your average expected total sum of all the rewards, in many cases discounted rewards? That's our V. And then Q is the same thing, but this is for state action pairs. So if I'm in state 17 and first action I choose is move left, then what is the total set of returns over time that's expected after that initial in this state and move left? So those we'll talk about V and Q a little bit today. We have the Bellman equation, which basically says that if you're talking about the value in a particular, we're using V here, but you can also do it for Q. The value for a particular state, then that is really just the sum of all the values, the long-term returns that you can get from the different actions that you take from here and the different states that you wind up in when you take those actions. Visually, you can think of it as a tree, and you're just summing up the returns from all the different branches. The branches on the actions you take, as well as the branches due to the environment, just perhaps having some randomness in it and where you might wind up. There's also the optimality equations. The Bellman equation is always true, that the return from a given state is just the sum of all those things. When you have an optimal policy, the best possible policy, then additional things are true, because basically you're saying, I know that whatever I'm doing, it must be the max. So for states, it's the max of the return and future, the reward and the future returns from the successor state. And then for state actions, it's a similar thing where you take the action, you wind up in a new state, and then it's the maximum from all the actions that you could take there. So this allows us to express a value recursively. So in this case, our optimal Q function is expressed as a function of future state Q functions. And so you'll see that in almost all these algorithms, they use this recursive formulation in order to create iterative algorithms. So after we went over the introduction to how we formulate reinforcement learning problems, we talked about policy iteration. And basically, if you can evaluate the true value, and again, this is long-term returns, not just the reward from one step, um, for all the different states, then what you can do is you can alternate greedily improving your policy, so taking the actions that have the maximum value, and then with that slightly different policy, you can evaluate that and see what the value is for all the different things you can do, and then greedily improve. And if you alternate this, there's a theorem that says that it will ultimately converge to the optimal policy. There's a diagram here, which I didn't show previously. I don't necessarily love this diagram personally, but I've seen now that pretty much every reinforcement learning course video uses this. So I'm concerned that maybe I'm the outlier, that I'm the only one that doesn't like this diagram, that it's useful for many other people. So I decided I ought to include it. And so the idea here is just, if you imagine a mere two-dimensional space, and this top line represents the different policies, and this, the different value functions. And then this bottom line represents the different policies. That what you do is you do your evaluation in order to figure out where you currently are in terms of accurately knowing what the value of your current policy is. Then you change the policy in order to be greedy with whatever the best values are, the best returns are, that you can see from where you are. You can't see all the way to the optimal policy, but you can see a little bit closer. And then if you then accurately estimate the value from your current policy, that moves you sort of over, and then you can so this is sort of a visual representation of, if you alternate evaluation and improvement, how it eventually gets closer and closer and closer to ultimately the optimal policy. So if you like this visual, and that helps you, great. And if you don't, then like me, you can ignore it. And so we're going to use this generalized framework of policy iteration, where you have some kind of evaluation and some kind of improvement. And as long as you alternate these in some sort of fashion, then the theory says if you do this infinitely long, what'll happen is you will get better and better knowledge of the values. When you have better knowledge of the values, then you'll know the better knowledge of which are the good actions to take. And so you'll have a better policy. And then when you have better policies, then again, you need to know the knowledge of what the value of those is. And as long as you keep doing this, that all of these things will converge eventually to an optimal policy. Because our goal at the end of the day is, right, we want smart agents. We don't just want to know what is the value of me playing chess this particular way. We actually want a really smart chess player. That's the kind of thing we want to do. So that's the stuff that we've talked about. And with this foundation, we can come up with different algorithms for how do we actually calculate the values. We can come up with different algorithms for how do we improve our policies and ultimately find optimal policies for the different situations, whether they be games or running a power station or whatever. So we're going to use this. We talked about dynamic programming, we talked about Monte Carlo, and so today we're going to talk about temporal difference learning. All right, any questions or comments before we jump into temporal difference learning? All right, awesome. So today, hopefully we can, there'll be a little bit less in terms of slides and formulas and content. There's just a few of them that we have here up front, and then we can hopefully get to the point where we're talking about the algorithms and seeing if you guys can really get a good intuition for how these algorithms work. So when we talked about dynamic programming, we have this update rule here at the top. And this complex formula, basically what it's saying is, from a given state, I have a bunch of different actions that I can take in my policy. And the environment is then going to wind me up with some sort of reward and some sort of successor state. If, in the case of dynamic programming, we have a perfect model of the environment. So for every state and action that you take, you know exactly what the reward is you're going to get and the probability that you're going to wind up in whichever successor state. then you can just mathematically, crunch through all of this. And so you can say for any given state, so let's say I'm in state 5 here, I have a bunch of different actions I can choose. And I'm going to wind up with a particular reward here, and then I'm going to have the value in my successor state. I can just sum all of these up, and that will give me a new approximation for what the value of state 5 is. So what we're doing is we're going completely wide. We're looking at all the possibilities coming out of state 5, but we're only looking one step ahead. Okay, that's the dynamic programming way of looking at things. And the update says basically, if you sum up all those things, you'll get a slightly better estimate than the one that you already had. Monte Carlo takes a very different approach. What Monte Carlo says is we're not going to go all the way wide, and we're not going to look at all the different possibilities from state 5. Rather, if you're in state 5, Monte Carlo's going to say, just keep going until you get to the end of the episode. And we're going to see what the actual return was from all the actions you took starting in state 5. So we're not going wide, we're going completely narrow. We're just sampling one possible trajectory through time until we get to the end of an episode. And then if we just keep track of all of these, we can average out what all the returns are. So again, dynamic programming goes shallow, but very wide. Monte Carlo goes narrow, but very deep. And what we're going to look at next is temporal difference does the short thing in both directions. It goes both shallow and skinny. Okay. So just a quick update here. So if you were iteratively calculating the mean when you get different returns in Monte Carlo, then for the first return, you would multiply it by 1. For the second one, you'd multiply it by a half. For the third one, you multiply it by a third. And if you keep multiplying by 1 over n, that will basically give you a perfectly accurate mean over time. Instead of having this changing multiplier here, which is 1 over n, we can do a constant step size. Okay, so this is like a learning rate kind of a parameter. And there's a couple reasons why you might do this. One is it's computationally a little bit easier, but then also if you have an environment that's not static, if you don't have a stationary environment, then it's actually possible that the rewards you're getting will change over time. If that's the case, then you don't want this thing here to keep getting smaller and smaller and smaller and then really tiny. So by the time you're doing your 1,000th, trajectory starting in state 5, whatever reward returns you get from that, you're only going to multiply by 1,000th in order for it to contribute to the mean. So if you use a constant step size, then what happens is it's like this exponentially weighted moving average. And so more recent entries count more than older entries. And that actually works well for a non-stationary environment. But the reason why we're talking about it here is because this is actually a nice segue into temporal difference learning. So again, dynamic programming, we look one step ahead, really wide at all the possibilities. It so happens in that case, you have to know the dynamics of the environment in order to know all the possibilities. But conceptually, it's wide, but only one step ahead. Monte Carlo is narrow. You only look at one action down each way, but you're going all the way to the end. So what if we did the shortest possible thing? We only did one step ahead, and we only sampled one possible thing instead of going fully wide. So that's what we do in temporal difference learning. Okay, so in Monte Carlo, the update that we do after a full episode is we say we have our estimate for what the value for a given state is. I've been saying state 5. And what we're going to do is we're going to add to it is some small number alpha times the difference between what the total return was until the end of the episode minus whatever our estimate was. So this is the error term, right? Saying, here's what we actually got minus what we thought we were going to get. So if our current estimate for the value from state 5 is 0.7, and when we did all of this We play till the end. Let's say it's, game. We play to the end of the game, and the new value is 0.75. Well, then it's like, okay, 0.75 is a little bit higher than 0.7. So we're going to take the difference between the two, 0.05. We're going to multiply it by our small parameter alpha, and then we'll update. And so then our new value will be something like, 0.71 instead of 0.7. It's going to go up a little bit. And we'll just keep doing that each time. But if you recall, sort of what is the return over time, from a given state, from state 5? Well, what it is the reward you get from your immediate action plus the discount factor times whatever the return is for, the state that you wind in after that. And so that's what the temporal difference learning update does. It says, okay, I'm in state 5. I take a single action. And let's say I wind up in the state 9. Okay, I get a reward and I wind up in state 9. Then I can simply say, if I add my reward to the discounted value that I currently think state 9 is worth, and I subtract that from that my current estimate, then that's basically telling me how much to tweak my estimate for state 5. So I tried to kind of talk through the thinking behind this, as well as just sort of this formulation of Monte Carlo's total return. But since we're not going to get to the end, we won't really know the full return G. But what we can do is, after one step, we can say, yeah, we know the return plus the value from our successor state. So let me pause here and just see if you guys are with me. Do people have questions? Does this make sense?
Yeah, that makes sense.
It does. It is just, the arrow will be very big. So I'm interested in where it goes.
So that's one of the real questions is, okay, well, you can do this, but is it actually going to work? I don't have on the slides here something that proves that it's actually going to work. What I can tell you, though, is in practice, it really does work. And in fact, it ends up working better than Monte Carlo for a number of reasons. All right. So let's just take a look at what this would look like in terms of just sorry, I've got another slide here. I forgot comparison here. So here's our update formula. All right, and again, like Monte Carlo, temporal difference doesn't require knowledge of the environment dynamics, so we don't have to have a perfect model of the problem. We sample from experience, so in every case, we are sampling, we are taking one action. We're not looking at all the possible actions, we're just taking one. It's different from Monte Carlo because it updates after every step. It's not waiting until you get to the end of an episode. And another difference from Monte Carlo is that it bootstraps. So in the case of, if I remember what I said earlier, we were estimating the value for state 5, and we took an action and wound up in state 9. Okay, so we're using our estimate of state 9 plus the actual reward that we got to slightly update our current estimate for the value of state 5. And so what's happening is that these actual rewards that you're getting are a really important part of the overall return that you're going to get. You can imagine that if you were in a state that's just one step away from the terminal state. So you're one step away from the end of a game, let's say. It doesn't matter whether you do Monte Carlo or you do temporal difference learning, you're only going to take one step before you get to the end of the episode. The two of them are effectively going to be equivalent, all right? And I think it's probably intuitive that if you're one step away from winning or losing a game, let's say, that you're going to have a pretty accurate estimate of how valuable is your current position, your current state, all right? So now let's take a look at something that's 2 steps away from the end of a game, all right? In the case of Monte Carlo, what you're going to do is you're going to play things out, which will take 2 steps. And you have to decide, how much credit am I going to assign to the last state, and how much am I going to assign to the second to last state? And as you get further and further away from the end of the episode, you kind of have this problem where you don't really know which moves you made along the way. Let's say you're 20 moves from the end of the episode. Which were the good moves that contributed to you winning? Maybe there were some really bad moves mixed in there, and you should have been able to, win in 5 moves, but because of that bad move, it actually took you 20. So there's this sort of credit assignment problem. If you can imagine temporal difference learning working your way backwards from the end, the last move before you get to the end is going to have a very accurate view, because it basically knows, hey, if I do this, I win. If I do that, I lose, whatever. Well, the second to last move, because it bootstraps, okay, it's going to base its value estimate on the return plus that super accurate value you have for the last state. And when it updates that, then basically you can imagine the third to the last move is going to use the reward plus a pretty accurate estimate from the second to last move. And so you can imagine that over time, basically, as you work backwards from the end, with temporal difference, you can actually get a pretty darn accurate estimate. And ultimately, there's a proof that says that, yes, it will converge to the correct value, just like Monte Carlo converges. What's maybe not intuitive is that because it's updating along the way, it's actually updating much more frequently than Monte Carlo. And in fact, temporal difference not only does it work, but it generally converges faster than Monte Carlo. I don't know, did that help just in terms of some intuition around it?
Yep, that was good.
All right, so let's take a look. So let's take a look at how we could implement what we just talked about to calculate the value function V for a given policy. Okay, this algorithm is called TD0. The reason for the 0 becomes apparent later. We're actually not going to get into that today. But so you can pick any policy you want for the particular problem. You pick your alpha, between 0 and 1. Typically be a small number, but it doesn't have to be super small as long as it's, 1 or less. We're going to arbitrarily initialize our values. A common thing is that we initialize everything to 0. So we're going to do a bunch of episodes, and in these episodes, what we're going to do is we're going to start in some state, and we're going to pick an action based on our policy pi. All right. So the policy says half the time go left, half the time go right. Then we're going to flip a coin, and we're going to pick whether we go left or right, 50-50. But we're only going to pick one. We're not sampling the whole thing. Just at any one given time, we're going to pick one. And over time, we expect that all the different actions will get taken. We then take that action, and then we find that we get a certain reward, and we wind up in a new state. So the new state we'll call S prime. So from this, we say, oh, okay, we have an estimate of what is the value for this new state S prime. So we simply add our reward and this estimate, and we take the difference between that and our current estimate, and that's our update. So now we're in our new state S prime, and we set this to be our current state, and we just go back to the loop, and we just do this over and over and over and over and over again. And so it doesn't really, this TD0 algorithm doesn't really treat whether you're sort of at the beginning of an episode, the middle, or the end. It doesn't really treat it any differently. It's really just simply saying, if I have a somewhat good estimate for my successor state, I have a perfectly accurate value for the reward. So if I'm in state 5 and I do this 10,000 times and I get 10,000 different rewards, I'm going to have a very accurate estimate of what the reward is because those are real, okay? Those are coming from the environment. And so if I take that very good estimate of the reward and I add it to my discounted value from my successor states, then that should give me a pretty good estimate for what state 5's value should be. And that's the way temporal difference learning works. So it updates much more frequently. It's updating after every step, whereas you could imagine Monte Carlo, if you're playing chess and there's 100 moves, you're only updating things after all 100 moves have been completed. All right. Any questions about TD0?
Well, not TD0, but I was thinking we can adjust alpha along the way. And I wonder if they discussed it.
Yes, I don't think that's a common thing. I'm just trying to remember. I don't think I've seen that much. There are certain times when you want to do things, and so we'll see that, like, if you have an epsilon greedy algorithm, you tend to shrink epsilon over time. But in this case, there's not necessarily a need to change alpha. Thanks, Maya. Any other questions or comments? Okay, so I've kind of talked through some of these, but what are the advantages? Because you'll see that basically today in reinforcement learning, I don't know, 75% of everything that's out there is using temporal difference learning. All right, there's this other policy gradient stuff that we'll get to later. It's a little more complex, but um, um, so why is everybody using TD? Nobody's really using Monte Carlo to solve real problems like backgammon, chess, Go, whatever. Not the simple Monte Carlo we talked about. So TD is naturally an online incremental algorithm. So basically, it is very easy to implement. So basically, if you've got something and you're just playing a game, you're experiencing the environment, you can, while it's experiencing, just keep updating, keep learning. So it's very easy in that sense. Waiting until the end of the episode is often just too long. You have these really sparse rewards, and it makes it very difficult to get accurate updates for the Monte Carlo algorithm. And then if you were here for the Monte Carlo session, we often want to do off-policy learning. And so that means that we're doing some sort of policy that explores in order to make sure we're checking out all the different possible states and actions. But when you have that, you have a problem with estimating accurately what the returns are under your desired policy because you're not following that. You're actually following a different one that explores more. Well, importance sampling from a mathematical perspective solves that problem, but in practice, it doesn't work very well. So if you say that I'm just going to use the ratio of how often I do this in my behavior policy versus how long I'm trying to do it in my real target policy, after a couple steps, if any one of those two policies differs a lot, then you can get your ratio to be 0 or super close to 0. And so if you do this and you wind up with a whole bunch of ratios that are basically 0, then that means that there's no update whatsoever. So importance sampling breaks down whenever your behavior and your target policy, if you think of them as like probability distributions, when they don't really have a lot of overlap, then you're basically not doing updates. So that's why importance sampling doesn't work in practice. As I've said, in practice, TD does actually converge faster. And there's an example, 6.4 in the book, that shows this subtle difference between Monte Carlo and TD. And I think maybe we'll actually take a look at that because that might sort of help explain, where is my book? Explain the difference between like why does TD actually work? How does it actually work faster? Let me see if I can find it real quick. Here it is. All right, so I'm not going to read through the whole thing. The main thing that I just want to show is this set of 8 trajectories, okay? So you're in a very simple Markov process, and you play through it 8 times. So once you go from state A, you get a reward of 0. State B, you get a reward of 0, and then you're done. The other 7 times, it's just state B. You get 6 ones, and you get 1 0. All right. So the question is, what should be the values? What are your estimates of the values for state A and for state B? So if you guys are understanding this, you know, there's a total of 8 times when we went through state B, and we got 6 ones and we got 2 zeros. So does it make sense to you guys that our estimate for what's the value of state B, we pretty much should all agree it's 3/4? You guys good with that?
Yep.
Okay.
6 divided by 8, basically.
6 divided by 8, 0.75. So there are actually 2 very reasonable answers we can come up with for what will be our estimate for this value of state A. Anybody willing to just give a stab as to what you think the value for state A should be?
Well, it seems like one estimate would be 0.
Yeah. So the Monte Carlo way of looking at it says I have one trajectory that went through state A, and it got a total return of 0. So my estimate is 0. And even if we were doing, we haven't really talked about this, but even if we were doing replay and we replayed through this a million times, you still, even though you're going to see this a million times, it's still going to be a million identical A0, B0, no reward whatsoever. So your estimate for the value of A will be 0. Is there another number, though, that might make sense? So the other way we can think about this is we can take advantage of the Markov property. The Markov property in this case, so the Markov property says that anytime you're in a state, it doesn't matter how you got there. The value of a state is the value of a state. So we just said that we agree that the value of state B is 0.75. So if A takes you to state B with 0 additional reward, and B is worth 0.75, then the value of A can be estimated to be identical to the value of B. It could be estimated to be 0.75 also. Neither of those is per se a right or a wrong estimate. But actually what is happening is when you use Monte Carlo, imagine that this was like a supervised learning problem, and then you had this as your training set. Well, if you ran gradient descent on this, basically what you're going to get is you're going to get the value for A is 0 because this is your example that contains A. The temporal difference way of looking at things would say, but I know the Markov property, and if you say that A is worth 0, but it always goes to B, and B is worth 0.75, that doesn't make sense. That's not intuitive. And so what Markov, what temporal difference is actually doing behind the scenes is it's actually figuring out, and forgive me if this doesn't make sense, you don't have to follow, but it's actually figuring out the maximum likelihood Markov decision process that would fit these trajectories. In this case, it's really straightforward because it only sees A goes to B, so it just assumes it's a very simple thing where A goes to B 100% of the time. But so if you assume that this Markov decision process goes to B 100% of the time, then you can not only estimate the value of A based on the trajectories that included A, you can also base it based on what your knowledge of the value of B is. And so I would say that that both answers 0 and 0.75 are fairly intuitive to me, but I can say that part of me likes 0.7, knowing this is a Markov decision process, right? We've said this is modeled as an MDP. I kind of like the 0.75 answer better, and that's the temporal difference answer. That's the TD answer.
So Ted, I'm having a little bit of a thought in this. This is probably inaccurate, but is it worth differentiating between the value of the state and perhaps the incremental value of a state? Because I think we can, in my mind, I'm sort of looking at it from the point of view of the incremental value of starting in state A is 0. I might as well just start in state B. But per our equations, you're right, the value of A is equal to B because I always go through B, right? However, if I was a rational human being and I had a choice of where to start, I would start in B, right? I wouldn't bother going to A because it has 0 incremental value. So is it worth even bringing that up? And I know we haven't touched on it anywhere so far, but is it worth bringing up incremental versus total value?
Incremental is a perfect way to describe it, Stephen. So, so I like what you just said, because to me that's actually more intuitive than the formalism. Okay, but basically incremental. Let me go back one more slide. Incremental basically says here's state A, okay, and this is our total return from it. It's just the reward plus whatever we're going to get from state B incrementally, right? And if this number is 0, then what you're saying is state A is not worth any more than state B is worth.
Right.
If this number were 2, then you'd say state A is worth 2 more than whatever B is worth.
Yep, agree.
Okay, so I really like the way you said that. And so the update basically says, gosh, if I had a pretty good estimate for state B, then if I add just what my reward to it is, then that's, kind of what our new value is. And then we just subtract our old estimate in order to turn this into an update rule. But that's basically, this is the Markov property fundamentally that TD is taking advantage of. It's saying that I can think of the value of A as being incremental based on the value of B. Monte Carlo does not take advantage of that at all. It simply just says, let me average up my trajectories. Now, I will say, this is a hand-picked kind of extreme example. In real life, you would hope you would have as many trajectories with A as you have trajectories with B. And then it would probably tend to be less of a problem. Okay, if we had 8 trajectories going through A and 8 going through B, it would be less of a problem. But I think hopefully from this hand-picked example, you can see where even when you don't have a lot of trajectories through A, the fact that you had trajectories through B helped you get a better estimate of A. So this is why in general for TD, some of your states are going to have better estimates, maybe because they're closer towards the end, and those are going to help the ones that aren't necessarily as good, even if you don't have a ton of examples for those other ones. So hopefully that makes sense and gives you guys some intuition. And I'm willing to take the time on this because, again, like I said, the majority of papers that you read in reinforcement learning, the majority of the announcements, the cool algorithms that you see, it's tweaks. It's actually not even tweaks, I would say. It's sort of refinements of TD. So TD is sort of like the boss. It's the thing to know if you want to know reinforcement learning. Okay, so now I'm just going to talk through a quick point here. So we showed temporal difference estimating the value function for states, so our V function. So if I ask the question, can you, using TD0, which we just showed, can you now plug it into policy iteration where you alternate between evaluating what's our current policy and then running improvement and then do evaluation again and improvement? And the answer is you can't just take this vanilla TD0 for state value functions and run policy iteration, because the improvement step says we're going to greedily choose the best actions. If you don't know the environment dynamics, then you don't know what the reward is that you're going to get, and you don't know which states you're going to wind up in next. Okay, so we can actually do this for small problems where we actually know the dynamics. But for the general case, and for one of the advantages we said is that you don't have to actually know the model dynamics. You can't do this. So instead of using the value function v, what you really need to know is you need to know the state action value function. You need to know q. All right. So the previous example, we showed v just because it's a little bit simpler. It's a little bit easier to understand. But we're now shifting gears and we're saying these real algorithms, they don't estimate v, they estimate q. And the update rule for q, it's very similar. It's just looking one step ahead, but the syntax is slightly different. So, you know, the update rule says our new estimate for q is just going to be our old estimate plus a small fraction times whatever our error is. Okay, what is the error? The error is the reward plus discount factor times the q value for the new state and action that you wind up in. And then from that, you subtract your current estimate. Okay, so for the most part, we've just replaced every v with a q. Okay, but again, the idea is we're not waiting until the end of an episode. We're simply saying after you take an action, you get a reward, and then you wind up in a new state. We're not going to use the value function v from that state because, again, we're trying to do this recursive formulation where we say our new estimate of q is a function of our old estimates of q. So then we only need to have one function q. All right. Any questions about shifting gears from v to q? All right. So now if we say we're going to use q instead of use v, now we can show real algorithms that work on actual somewhat hard problems. The first of these is called SARSA. And what this algorithm does is it simply does value estimation, okay, of the Q function for a given policy. And then it does policy improvement. Okay. Oh, I have a typo here. This should say improvement. It does policy improvement, and then it does estimation and improvement. This is our generalized policy iteration. Okay. It's exactly what we talked about. And so I'm going to go through this algorithm first, just at a high level, before I go through all the details. So we initialize everything. Our Q can be all zeros. We here are potentially using like an epsilon greedy policy. And so what we're going to do is we're going to start each episode in some state. We're going to pick an action. We're going to take that action. Now we're going to wind up in a new state, S prime. And from there, there's this little funky thing that has to happen is we have to pick our next action, our A prime, because in order to get a value out of the Q function, you have to have both an S and an A. And so based on that, we don't take that next action, but we just do have to pick it. Okay, so based on our policy, we pick the next action. And so then we do our update rule. We simply say our estimate for what the long-term return from a given state starting with action A is our old value plus a small amount times the difference of our new estimate, which is the reward plus the successor state in action, minus our current estimate. And then we simply reset and say, now this new state is our starting point, this new action is our starting point, and go back up. And so if you sort of look at the way this algorithm works is you start with the state S, you take an action A, so now we're SA. You observe the reward that you're going to get, that's an R. You wind up in a new state, that's another S. So now we have S, A, R, S. And then we have to actually pick an action that we're going to take next in order to get the new Q function. And so we need an S, an A, an R, an S, and then a new A in order to do our update. And that's how you get the acronym SARSA, because you start with a state action, you see your reward, you pick your new state action, and from there, you have enough information to do the update. And so SARSA is just an acronym for state action reward, next state, next action. All right, so at a high level, this is the SARSA algorithm, and this algorithm really works. This is a good algorithm. One thing you might notice, though, is there's no explicit policy improvement. When we did Monte Carlo, you would see, it would say, loop for a while and evaluate this policy, and then once that converges to an acceptable level, run one-step policy improvement, greedy policy improvement. And then from that new policy, then run evaluation for a certain amount of time, and then do a single-step policy improvement. You'll notice that there is no explicit policy improvement in this SARSA algorithm. Does that make sense what I'm saying? Like, hey, wait a second, you said we were going to alternate evaluation improvement, but you haven't actually shown me any improvement. And so the reason for that is that because we have a Q function, not a V function, it's really easy to see which are the best actions. It's just the action for any given S, right? If you've got 4 different actions that you can take, you can just see the Q value for all 4 of them. So it's implicitly embedded. If we say that we're choosing actions using something that's epsilon greedy, okay? If we choose an action that is 100% greedy, that is greedy policy improvement. The only reason why we choose epsilon greedy here is because we want this algorithm to explore such that it will randomly, with a certain probability, try every action from every state over time, and then we'll have good estimates for all the different actions. If it weren't for the fact that we needed to explore, you don't even need to be epsilon greedy, you could just be fully on greedy. And so this is where Maya asked earlier, do you maybe change your value? And so yes, typically in the real world, what you would do is you would start with a high value of epsilon. You'd want it to do a lot of exploring early on, and then epsilon can shrink and shrink. And then SARSA as a on-policy algorithm, because it is exploring, it is technically not finding the optimal policy for the original problem, it's finding the optimal epsilon greedy policy. And so if you can shrink epsilon, then ultimately the two are the same thing. And of course, that's a problem because you don't know how long do I wait before I start shrinking epsilon? That's sort of unknown. But nevertheless, in theory, if you shrink epsilon smaller and smaller and smaller, then it converges towards the true optimal policy. But in a few extreme cases, exploring can have some bad side effects. And so there's an example in the book where you have a grid world and there's this cliff with this terrible -100 reward if you fall off the cliff. Well, if you're doing epsilon greedy, where sometimes you just take a completely random move, if you're next to the cliff, even though you may have fallen off the cliff before and you've learned that's really bad, epsilon greedy says sometimes you take a random action and you just fall off the cliff over and over again an infinite number of times over time. But so that's the reason why you no longer see an explicit policy improvement step, is because when you have Q, you can just use epsilon greedy policies, and implicitly in that is every time you are maxing out, unless you flip your coin and you get a number less than epsilon, but you're always taking the max from that. So does that make sense? Are you guys
kind of cool.
following SARSA?
Yeah, makes sense.
Yeah. So it took us a bunch of theory early on and Markov decision processes, but this is a very simple algorithm to write. So for basically any kind of environment that you're in, so let's just say the self-driving car, all right? I'm not saying this will learn every possible situation for driving a car, super fast. But in terms of writing this algorithm, like, it's easy. Whatever your time step is, I just choose my action. I go ahead one time step. I say what my next action will be, and boom, now I have enough information to run this update here, where I just say reward plus gamma times my new Q estimate, and this sucker will provably converge. For a self-driving car, the problem is the time to converge might be, 800 billion trillion years, but it will converge. So this is on policy, and our explore exploit dilemma for on policy algorithms means that we're often doing this epsilon greedy business. So wouldn't it be nice if we had an off policy algorithm for temporal difference learning? So 1989, Watkins comes along and develops an off-policy algorithm for temporal difference learning called the Q-learning algorithm. This is the most important, most famous algorithm in reinforcement learning. So the tweak that he makes to SARSA is that in SARSA, we said we start with a state and an action, we see our reward, we wind up in a new state, and at that point we pick one action based on our policy. In Q learning, we're not just going to pick one from our policy, we're going after Q star directly. We are going to look at the max of all the different actions that we could take from our new state S prime. And we are going to immediately chase the best one, our current estimate of the max. Okay, so what we can do is we can take actions from our initial state S with some sort of epsilon soft, say an epsilon greedy policy. And what we're actually learning is not the values from that, but rather the optimal values where we're taking the max. So the update function for Q learning, how it differs from the TD0, from the SARSA algorithm, is there we picked one action and we just simply said, Q of S prime comma A prime. But so we replace that single action with a look at all the possible actions A, and we take the max from that. So even though in our next time step, we might not actually take this particular action A that's the max. Even though we don't take it, we still know based on our Q table, we know our estimates of all the different possibilities. So imagine again, some grid world, we can go left, right, up, down, and we say left is worth +10 and all the others are worth -1. We know that left is best. It doesn't matter whether we actually, in terms of experiencing the environment, now do left, up, down, what we do. We can simply say that the estimate, the update that we're doing is based on the fact that our current estimate for left says it's a +10. It's a really, really good action. And so Q learning converges way, way, way faster than SARSA because it's taking advantage of the fact that it knows. Now, again, we're not saying that we know the model dynamics. We're simply saying, hey, when it comes to choosing actions, we have a policy, but we don't have to follow pi, our current policy. We can just take the max and immediately chase the biggest rewards. Is that making sense, sort of the difference between Q learning and SARSA?
Yes.
All right.
I think what I'm taking away from it, Ted, is that this Q learning basically says that I'm going to be greedy in state T+1, completely 100% greedy in state T+1. That's kind of what I'm.
You're being greedy in terms of the value that you're estimating for T+1. You don't have to actually take that action. but you're going to be
Correct, right.
greedy in using that in terms of
As an
now
estimate, right.
estimating.
Yeah.
You use the wonderful expression, it's incremental, right?
Yep.
But so instead of saying, hey, I got a reward of 3, and so I'm worth 3 more than the next, action I take. Now you're saying I'm worth 3 more than the best possible action I could take.
Yep.
So what does this algorithm look like? It's actually surprisingly compact. This algorithm says we initialize things. You start in a state S. You choose an action, and again, this action you may want it to explore, because you want to, over time, infinitely try all the different states and all the different actions. Okay, so you use an epsilon greedy policy, let's say. Once you start in a certain state and you take an action, you're going to get a reward. You're going to wind up in a new state. And from there, our update is we take our current value, we add a small amount, which is based on the difference between, and then again, instead of the next action, it's the best of all possible next actions plus the reward. And that's all you do, and you loop. And so, in fact, what I showed for SARSA is you don't have an explicit policy improvement step. For Q-learning, not only do you not have an explicit policy improvement step, but even though it's off policy, you don't even have an explicit behavior policy that you're saving. Now, you could if you wanted to, okay? But you don't even need to. If you just use an epsilon greedy policy off of Q, it's derived from Q, then basically on the fly, you're deriving your behavior policy from Q. And so it has no more memory requirements. Even though it's off policy, it has no more memory requirements than SARSA did as an on policy learning algorithm. So Q-learning basically says you get all the benefits of SARSA, no more memory. I don't have to worry about epsilon greedy convergence. I now have convergence to the true Q star, and it actually converges faster. It's like all win and no trade-offs. So that is why basically Q-learning is, again, I'm throwing out wild estimates. I'm learning this stuff too, just like you guys. But I'll just say Q-learning is the basis of like 3/4 of all reinforcement learning out there today, because this algorithm, we said TD is better than Monte Carlo. SARSA's, TD. This is like way better than SARSA. So this is at the core of most RL that you see out there. Any questions?
Yeah. Are these methods as efficient to implement, or are we throwing more and more computronium at the problem until it goes away?
If you look at this, you'll see this is a pretty darn short set of pseudocode. So basically, the only thing that we need for this algorithm, okay, because like alpha and epsilon are just scalars, okay, gamma is a scale. The only thing we need is we do need a table for every state action combination. So let's say you're doing a Pac-Man game and there's 4 actions at any given point in time, left, right, up, and down. So the number of actions is relatively small. Well, what if I were learning from pixels? All right. And so if each pixel, gosh, I don't even remember how many colors they had, but I'm just going to use some approximate numbers. Let's say that there's only 100 colors possible for each pixel. And the pixels are something like 200 by 50 for round numbers. So 1,000 pixels. All right. Well, that means that there's 100 to the 1,000th power different combinations of all the different pixels. That is going to be a problem creating a Q table that has 100 to the 1000th power times 4 different entries. Right. So 4 columns for the different actions and 100 to the 1000th power rows.
So it's pretty clear that, human beings employ some kind of natural abstraction and pattern matching.
Yes, you absolutely need to strike. Now, in theory, I could take something like an Atari game, like Pac-Man or whatever, and I could reduce the dimensionality quite a bit by saying, look, we're not learning from pixels. I have knowledge that there's the little, I don't know what they're called, the little dots that Pac-Man eats, and there's the power-up ones in the corner, and there's, where the position of Pac-Man, the position of the ghost. So I could reduce it, but it's still actually going to be a pretty large thing. So ultimately, that's where you will see where we're going next is this is a wonderful algorithm. This is still the algorithm that's being used, but we're going to switch from having an exhaustive table with one row for every single state action combo. We're going to use an approximation function that tries to, basically, if we pass in a state and an action, it'll return a value, okay? But it's not going to do so by keeping track of every single possible combination. What it is, it's going to be a function that approximates that table. What do we have in machine learning that, given a table of labeled values, spits back an estimate? It's supervised learning. And so basically what we do is we just simply use a deep neural network in supervised learning mode to estimate Q. All right. And so again, if we had a full table, if it all fit in memory, it is Q learning. If instead of having a full table, we use a neural network, this now becomes deep Q learning. And so basically you now have DQN, the big aha deep learning algorithm in reinforcement learning. That's where we're going. Did that answer your question, Adam?
Yeah, so basically you make that neural network, and it's that feeling you get as you're playing the game of, oh, hey, I'm in a good position, or ooh, this isn't a good position, right? And
and so as a function approximator, right, what you want is that deep neural network to be able to figure out which of these different states and actions have very similar values and collapse them together, right? And which ones are different. And so hopefully your deep neural network learns well, and so it learns to separate the places with high values from the ones with low values and do a pretty good job of estimating.
yeah, he's got to get him the premium Cheetos and the nice gaming chair.
All right, I apologize, guys. I need to go do something with family here for a second. So I'm gonna go off camera, and hopefully you guys can talk amongst yourselves and share something about TD.
This is amazing. I'm so excited to have learned about all this. Does anyone here know a good place where I can try this stuff out? Maybe without having to spin up whatever ungodly amount of compute would be needed to actually train something like this?
So you could try one of the Kaggle courses, would be one idea. And then the other one would be Amazon has, I think, the Deep Racer thing, which is an online virtual car with, a camera and a couple of other sensors, if I remember correctly, where you can try implementing some sort of reinforcement learning. And they provide a lot of the framework for you. Now, interestingly enough, the one thing that I've observed in both the Kaggle and the Deep Racer things is most people don't really use reinforcement learning algorithms. They just use something they develop themselves, sort of a rule of thumb algorithm, like if you're getting too close to a wall, steer away from a wall kind of thing. if you veer too far off of the center line, steer back to the center line. So they don't use truly reinforcement learning approaches. But there's two places that I can think of.
And when you're saying that, is it because those models are just more successful than the deep learning, or is it just because there are a lot of people who don't happen to know deep learning and they go there anyway?
That's a very good question, and I do not know the answer to that. Well, I can tell you, I can give you the observation, right? The observation is I don't see a lot of reinforcement learning being used. I have no idea why.
Hey, Stephen, when you're talking about this place with the camera, I'm not understanding the word or the place that you're saying. Can you put that in chat?
So it's called, yeah, it's deep. If I remember correctly, I'd have to, yeah. Let me go do a little bit of research, but off the top of my head, it's called Deep Racer. And it's basically a little, you can actually buy it if you want. It's a physical little mini car that has two cameras on it. I think it has some sort of an LiDAR, no, not a LiDAR sensor, some sort of a radar sensor or something on it, blah, 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 blah. And then you can program it to move around and follow a track and do all that sort of stuff. Amazon, I think, also has the sort of digital twin of that, where they have an environment where they emulate in software that car. And that's called Deep Racer.
Okay, thank you. And I see somebody put it in chat, so thank you.
Oh, okay, someone be. Thanks, Kirk.
Yeah, sure.
Hey,
I
guys,
was
I'm
just
back.
gonna have to look for it myself.
So Ted, the question that came up, Adam asked, is there anywhere that you can go to kind of try some of this stuff out? And I answered that Kaggle would be one place, and then
Yes.
Amazon Deep Racer or AWS Deep Racer would be another one. And that's what we're discussing as you came back on.
Yes, and that is a nice segue, because next Saturday, what we're gonna, I decided what we're gonna do is we're actually gonna play around with these algorithms. I'm gonna find some small problems and show actually running these algorithms. So I've got some work to try to see if I can get some reasonable like head-to-head stuff, but I will be showing OpenAI Gym, as well as just some smaller handcrafted stuff that's from the book, like Blackjack and things like that. So thanks.
One of the things that we're discussing that was really interesting, since you're talking about that, is I remember, for example, from the review of the Halite Kaggle competition, most people do not actually use reinforcement learning approaches. They just use hard-coded algorithmic, this is what I came up with as a rule of thumb out of my head kind of thing. And that's what we're kind of discussing is, Adam was asking as a result of that, is that because, reinforcement learning algorithms just aren't very successful, or is it because people just aren't familiar with them? And the answer was, I have no idea.
So if you go to Kaggle and you look up the Halite game, it's actually a very hard problem. So the gist of it is you've got this small screen. I don't know what it was. It was like a grid, call it like 25 by 25 or something like that. It's relatively small in that sense. And you start out with a space station, you send your ship out, and there's just different squares on there where you can mine this halite stuff, and it's worth points. The thing that made it very complex is that at any point in time, you have a large variety of actions that you can take. So in addition to the spaceship moving around, and if it's on a square, it can mine, it has to decide at what point you don't immediately get value from the stuff that you mine. You have to return back to your base. And once you return to your base, then you unload all of it and you get the value from it. So that's complexity number one. You can turn spaceships into new bases. So like if all the halite that you want to mine is very far from your base, you can turn a spaceship into a new base. You can also, from a base, build new spaceships. So you can have more than one at a time. All right. So right then and there, that creates a whole lot of different options. And basically, there are these very tricky trade-offs because building a base or building a new spaceship has an upfront cost. So imagine, you take this -50 to build a new spaceship. You need to figure out, well, gosh, am I gonna, right? And so when you watch the game, it's clear you have to build new spaceships. You will lose the game if against any decent opponent if you only have one spaceship. All right, but so it's very hard to take those choices where you're taking that big negative up front because it's a long-term investment. And then on top of that, in order to make the game even more complex, it's actually a 4-player game. So you're not even playing head-to-head against another agent. You're now playing against 3 different other agents who could have conservative, aggressive, whatever type policies. So those are some of the core elements that made that an extremely complex problem. So I think even just the simple problem having no opponents, just, you know, when should you invest? When should you just use the ships and bases you have and you know, mine away? That would probably have been a fairly hard reinforcement learning problem just because of that space of actions. But so yes, so the plan is next week to at least show some simpler things like, you know, blackjack or some of these sort of toy grid world type environments. But hopefully then, yes, the discussion can kind of go off and maybe we'll check out some different websites and things just as people talk about other things that the highlight competition. There's an easier one now that's I can't remember what it's called, but it's Greedy Goose or something like that. But if you kind of remember the old video game Snake or whatever, but it's this idea where you you're moving around on a grid, and every time you eat something, you become one longer, and you don't want to crash into your own path, and you don't want to crash into anybody else's. So it's sort of like Snake Tron like game if you're familiar with those oldies. Okay, cool. So let me, since I'm checking the time, let me just quickly finish up. We have one more slide here. So if you look at the chapter in Sutton and Barto, there's a couple of things they talk about. They talk about expected SARSA, and not going to go into details, but in SARSA, what we did is we started with a state, we took an action, we saw what the reward was, and then we had that new state. And so Q-learning did a tweak on it where instead of just picking an action based on the policy, it picked the max action. Expected SARSA, instead of doing either of those things, says, oh, well, based on your policy, if you say a quarter time do this, quarter time do that, half the time do that, I can actually just figure it out the expected value. I can take the Q value from the first one, multiply it by 0.25, the second 0.25, the third one half, and then I'll have a very accurate expectation. So expected SARSA can converge a lot faster than SARSA. I'm sure there's more to that, but I'm just going to kind of leave it there. But the one thing that let me briefly talk about after states. So this is not a critical thing, but just so you know, if you're playing a game like chess and you choose a certain move, you know exactly what your next state is going to be. There's no probabilities, there's no whatever. It's always just boom. if I move my bishop here, that's then the new position of the board. That's the new state. And so anything that uses things like cues or games that have like moves, if you're 100% sure what the next state is going to be, then you can improve your algorithm by basically taking a look at the estimates for what that next state is going to be, since that's so that further down the road you have more information. So it talks about that at the end of the chapter. But the really cool thing, I don't know if cool is the right word, the really important thing that I think was introduced here is they talk about the double Q learning algorithm. And the motivation for the double Q learning is very important. So the motivation is that there's this maximization problem. And it is a problem with pretty much all RL algorithms, but it is definitely a problem with Q learning. So imagine that you had a state where you have 1,000 different actions that you could take. Lots and lots and lots and lots of different actions. All of those actions actually have a mean return of 0, okay? But there's some randomness to it. They have a variance of 1. So sometimes you might get a positive, sometimes you might get a negative, but they all average 0, okay? If I were experiencing this game and randomly doing things and picking from these 1,000 different actions, I would have estimates for what's the value of all those 1,000 different actions. What you would expect is that maybe 500 of them would have some sort of positive number, 500 of them would have some sort of negative number. And then over time, you know, those numbers will sort of squeeze down and get closer and closer to zero. But initially, you know, I'm gonna have half positive numbers. Well, if I keep taking the max from this, I'm gonna have a lot of things, you know, I'm gonna have 500 of these actions that I estimate have positive value. And even as I take them more and more and those numbers come down, there's just so many actions that in general, whenever you take a max, you are biasing sort of your algorithm towards positive, you know, numbers. This is actually one of the key problems in general with reinforcement learning, is that if you're doing some type of max operation, they tend to be overly optimistic. So if you have any kind of environment where you can occasionally get a really great reward, is really easy for reinforcement learning algorithms to sort of get stuck and to vastly overestimate the value of that particular action for a super long time, if not forever.
That sounds a lot like human reasoning.
Yeah, I'm not sure if humans are sort of more biased towards positive or negative things. I think we actually, there's some formal name for, you know, having a negative bias. So like if
Loss aversion.
yeah, loss aversion, whatever. But I'm just saying, so like, you know, if you go to a certain restaurant and they have like the absolute best chocolate chip cookies, but like one time you go there and you eat one and it's like raw by mistake because they screwed up, you know, you might never go back to that place, despite the fact that the other 999 times it's the best chocolate chip cookie you've ever had in your whole life. You know, but these deep learning algorithms, they're, you know, they don't know what they don't know. And so they have this tendency, if they see some positive, to just really chase that hard. And it takes them a while to unlearn that. So the double Q learning algorithm actually sort of solves this particular issue, where you just keep two separate Q tables, and then you take the argmax in order to find the best. My estimate is that the best action right now is action 17. And then you use the second Q table to say what is the estimated value of action 17. And by decoupling that, then you take away this maximization bias. But maximization bias shows up just in other ways. It shows up in terms of bootstrapping. So when you're basing your value based on successor states, you still have this phenomenon where you have this tendency to pile on maxes. And so you're always just being a little bit overly optimistic. And so one of the things in reinforcement learning that I started to see in some of the literature is trying to have RL algorithms not overly estimate Q in general.
Okay.
So even though this is just sort of this brief thing mentioned at the end of the chapter here, it's a great introduction to one of the fundamental problems in reinforcement learning. So basically, all of these things really smart people have proved converge asymptotically to the optimal policy given infinite time and infinite exploration. But what we worry about is, do we actually have something that converges to something very smart in a reasonable amount of time? And it turns out that things like this maximization bias for certain types of problems cause the amount of time it takes to converge to be just way, 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 way too long. And as you get to harder and harder problems, then you just need things to converge even better in order for them to become tractable. And so that's why things like Go for a while were really hard, because Go has a lot of different positions on the board. And so there's a lot of options at every move. It's hard for you to, it's a big problem, and it's also hard to converge. And so you can find that these algorithms will get stuck and do poor things. And so if you look at state-of-the-art papers, they're probably doing, like I said, 3/4 of them are doing Q learning. You know the nuts and bolts. You now have all the basics for that. what they're dealing with is these weird problems like a maximization bias, or how to get it to converge faster, or how to be more sample efficient. I think Ryan mentioned that term a session or two ago. So in other words, does it take me 1,000 times seeing what to do if I'm playing blackjack and I have a 12 and the dealer's showing a 2? Or can I learn that in only 100 examples? Or can I learn that in only 20 examples? And so those are the kinds of issues that people are working on in terms of some of these more nuanced tweaks to the way they're doing. But at the heart of it, you will see that the ones that are not doing, you know, policy gradients, basically it's just Q learning. That's at the heart of it still. It's taking one step and doing an update. All right, so here's our recap. We reviewed the reinforcement learning basics, and then we used the temporal difference update, and we showed that without explicitly having policy improvement, we can still do generalized policy iteration. We can do SARSA, we can do Q learning. And here's our schedule. So next week, we're gonna play with some code examples. I'm gonna try and find some. If you guys have time, if you can find other examples, that'd be awesome. I don't think next week will be as formal as sort of these first few sessions have been in terms of just trying to build up the terminology and you know, level set everybody. There's a little bit of stuff in chapter 7 that talks more about TD learning. We're not going to do a full session on chapter 7, so we have a little bit of time. I may throw something a little bit in there, and then just as a advance notice, the week after that, we'll take a break for the July 4th weekend. So we'll skip that and come back on July 10th. All right. Thanks for sticking with us. Those of you who didn't have something else that you needed to run off to. Any closing comments or questions before we shift gears to the project discussion meetup?
I just want to thank, because you know, it was really beautiful that we started from pretty much scratch and got to this point.
Yeah, I am really impressed with this book. I see now why people talk about this Sutton and Barto book as being the Bible of reinforcement learning, because we really did start from scratch. And now we're at Q learning. And again, there are lots of refinements that people have done to it, but you know, we are really armed with in terms of reinforcement learning. All right, I'm going to stop the recording here.